So when we think about the reactions that halogens can undergo, we want to remember what key properties are going to be involved. And what's the most dramatically obvious property to bring up whenever we talk about halogens? Electronegativity. You can see here that the electronegativity for the halogens is going to be larger than nearly every element on the periodic table. Once you get partially down the periodic table, sulfur, oxygen, and nitrogen start to become competitive with the electronegativities that we have for these. But still, these electronegativities are so large, they're going to drive electron transfer processes. Now, as a result, that's what we're going to be talking about. These are going to be electron transfer processes at heart. Now, if we take a generic example, like a metal and chlorine, or any of the other halogen molecules, what we'd end up seeing is that we're going to have chlorine, and of course its Lewis structure looks something like this. There we are. And we're going to have a metal, and let's just assume for the moment that it's got 2 electrons that are reasonably accessible. I'll just point at these 2. We won't worry about where they came from for the moment. The chlorine bond actually has an electron living over here and over here part of the time, right? And that's why they were sharing these 2 electrons, was to make it so that they felt like they had the pair. But this is so electronegative versus what the metal has that it's going to steal one of these electrons, and so will this one, giving it an electron there, and leaving this as the metal 2+. And then, of course, these now negatively charged ions of chloride can pair up to the metal, and we'll end up getting a metal chloride. So if copper was our metal, and we had some copper sitting around some chlorine, like around a pool environment or something, we'd expect that we'll probably end up having some of that metal turn into metal chloride, or so copper chloride in this example. And if you remember from seeing it in the laboratory class, copper chloride is this bright blue-green color. If you've seen that color before around a pool, that's what was going on. It was actually the chlorine reacting with copper in order to form this copper chloride through an electron transfer process. Now if I clean this up, let's take a look at a second example. Now let's go for one that's middle of the road for electronegativity, and let's see what happens if we have H2 and Cl2, or any of the other halogens. I'll just keep on using chlorine as an example for that one for the moment. Keep these the gas phase as well. Well, let's go for a Lewis structure again. We know that hydrogen has only 1 bond, and that's all of its electrons. We're going to have that chlorine molecule that I showed moments ago, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Again, this represents 2 electrons. Chlorine is more electronegative than those, so that electron ends up coming over to here. That bond was representing electrons. Same thing happened over here. I now have Cl-, I have H+, and another H+. These 2 are going to stick together immediately and form HCl. Now this is happening in the gas phase, so all of this will still be in the gas phase. We'll have HCl, we'll have 2 of those, and they'll be in the gas phase. Now, later on, we're going to talk about what happens when something like HCl is dissolved in water. That's going to be a strong acid. But when they're in the gas phase, this is going to be a polar but covalent bond. And so they're going to stay together and float around in the gas phase. Now, what if we go for the most extreme other version? What if we take a halogen and put it with another halogen? Suppose we had Cl and Cl, and nearby we had fluorine gas. And of course, both of these will have their octets, as will both of these. And that doesn't look like a pair, so we'll redraw it. There we go. So what's going to happen? Fluorine is the more electronegative of these 2. So let's just go ahead and go for the freeze frame version where we have it look like that. This electron will be stolen up to here. This electron will be stolen up to here, giving me 2 F- and a Cl+. Cl+ is definitely not going to be a stable sort of thing. Halogens don't like to be plus charges. They're too electronegative for that. It's going to immediately latch on to the fluorine, trying to get its wallet back, if you like to think of it as a mugging. And so you'll end up having FCl, or ClF, whichever way you like. You'll have 2 of those be the product from that reaction. So if it's halogens, you end up having an exchange reaction. If it's hydrogen, you end up forming the gas phase version of an acid. And if it's the metal, you end up getting the metal chloride as a result. That's the sort of thing we're talking about with their halogen reaction.